Okay, class, today we're going to be talking about combination circuits. So in the last two lessons, we looked at series circuits and we looked at parallel circuits. So here we're going to take two amazing things and make something that's incredibly complicated and not fun to deal with. But we're going to power through it and we're going to figure out how to solve combination circuits. So here we have an example of combination circuit. So we have a part in the top that's parallel with two resistors in series here in the middle row of the parallel, and then that parallel part is in series with another resistor. And in this lesson, we're going to talk about how to break these down and how to be able to solve them and figure out what the voltages, currents, and resistances are for individual parts of this combination circuit. Now, before we start talking about combination circuits, I want to take a moment and talk about how we can compare and tell the difference between parallel and series circuits. So here I have drawn three different circuits. One of these circuits is parallel, one of these circuits is series, and one of these circuits is a combination of the three. So go ahead, pause the videos, look at them for a second, and try to figure out which of these three you think is series, which is parallel, and which is a combination. Were you able to figure it out? Let's look at each of these one at a time and try to explore whether we think they're series or parallel. So remember when we were talking about series that we talked about how there is only one path that the electricity can flow down. So the current flowing through the wire only has one option. It doesn't ever come to a fork in the road. So if we're tracing our first circuit, we start from our battery and we come down and then there's a turn and then there's another turn. And we go across this first resistor, there's a few more turns, go across the second resistor, there's a few more turns, the third resistor, and back to the battery. Notice how I could trace that without picking up my pen. So I can trace this circuit without ever having to go back over any spot or go back and revisit a spot and loop back around. And that means that it has to be a series circuit. Now this next example that I gave you is pretty straightforward. It looks fairly similar to the other parallel circuits that we have. One of the things that I talked about that's pretty emblematic of a parallel circuit is that you have these parallel rows. So these resistors are in parallel and they kind of look like they are parallel, but they don't have to be that way. But the way you really tell that this is parallel is you start tracing the way the electricity comes out of the battery. And once you reach this corner right here, I'm going to mark it A. At point A, the current has a choice. Does it go right and hit this first resistor or go straight and continue to the rest of the circuit? Then there's another split up here at the point that I'm going to mark B. At this point here, again, the current must split. It can either go to the right and go across the resistor or go straight and continue the rest of the circuit. And then if it continues the rest of the circuit, it goes across the third resistor. And then all of these currents recombine as they come across their resistors and go back into the battery. So this is going to be a parallel circuit. So by process of elimination, you might have guessed by now, Mr. Halberstadt, this has got to be a combination circuit, and you would be right. But the way we know this is a combination circuit is, again, we have to trace. So first, we want to trace coming out of the battery, and we see here at this first junction, we can either go down or we can go up. So if we go up, then we would just have one resistor to go across, and we come back down, recombine, and go back into the battery. But if we go down, the story's a little bit different. So if we go down this circuit and we take the bottom path, we come and we have one resistor, and then we follow the path and we have another resistor. So what we have here is a partial parallel circuit, because there's this option here where you can go up or down, but also there's a series circuit because these two bottom resistors are in series with each other. Because once you've chosen the bottom path, you don't have any other options. You have to pass through the first resistor and then follow through the second resistor. So this is a combination circuit, partially parallel, partially series. So what this boils down to is if you have no options of the path of the electricity, if it must follow one path from the start of the battery to the end, from the positive terminal to the negative, then it has to be a series circuit. If you start running into these junctions where the electricity forks and it goes either up or to the side, then you have a parallel circuit. And if you have a junction that leads you to a bunch of resistors together that are in series, then you have a combination circuit. So how do we solve a combination circuit? The biggest piece of advice that I can give you in solving a combination circuit is that you have to start from the inside and work your way out. So in order to explain what I mean by that, let's trace what the electricity does as we travel through this circuit. So we leave the battery and we travel around. The first thing that we run into is this junction right here. So at this junction, we either have to go up and around through R1 or to the right through R2 and R3. So this is what I would call the outside, because it's the first thing that our electricity runs into. Now, if we follow the top rung, the top route that the electricity can follow, there's only one resistor there. So there's not any sort of simplification we can do on that one resistor. So that we're just going to leave as is. Now, if we follow the middle route, though, we see that there's R1 and R2 in series. This is what I would call the interior part of it, because first we hit this parallel junction, and then inside the parallel junction, we have this series circuit. So when I say start with the interior, I mean start by simplifying this interior series circuit, then simplify this parallel circuit, and then you'll have this equivalent resistance in series with R4. You can solve that series circuit, and then you can get the equivalent resistance of the entire circuit. So let's do that. So we're trying to figure out the equivalent resistance of R2 and R3 in series. And so we know that we just add R2 plus R3 to figure out the equivalent resistance. Now, we're using the notation R23 to mean the equivalent resistance created by resistor 2 and resistor 3. Add together 40 and 80, and we get 120. Because we can say that the equivalent resistance of 2 and 3 is 120 ohms, in our diagram, we can just replace resistor 2 and resistor 3 with a 120 ohm resistor, like I have drawn. So now let's add in R1 so we can figure out the equivalent resistance of R1, 2, and 3. Because R1 and R2, 3 are in parallel, we have to use our reciprocal equation. 1 over R1, 2, 3 is equal to 1 over R1 plus 1 over R2, 3. Substitute in our values, find a common denominator, then solve. Again, we can replace R1 and R2, 3 with R1, 2, 3, the equivalent resistance of those three resistors. Now we're left with a simple series circuit that we know how to solve. We first add our resistances together. This gives us our total resistance, which is 150 ohms, and then we have to plug that into V equals IR. We end up with a current of 0.06 amps. Now, what does this current of 0.06 amps mean in relation to the initial circuit? So let's go back and look at our initial circuit. Where does our 0.06 fit in? Now, previously when we found the total current, that's always been the current coming out of the battery. So that's what we have here. Now, if we want to figure out the current going through R1 specifically, or R2 and 3, or across R4, well, we know R4 because we know these 0.06 amps have to come back around. So the current across 4 is going to be 0.06. But able to figure out what the current is in the other resistors, we have to learn something called Kirchhoff's rules. Gustav Kirchhoff was a German physicist who came up with 2 rules to help people figure out how current and voltages act in a circuit. So the first one that we're going to talk about is about Kirchhoff's rules of currents. He says that the current going into a junction will equal the current leaving that same junction. So in our example here, we have 3 milliamps and 2 milliamps coming into this first junction. So we know that the current leaving the junction to the right has to be 5 milliamps. And then if we continue and follow this current to the right, we know that that 5 milliamps has to continue, hit this second junction. We have 5 milliamps coming in from the right, 5 milliamps coming in from above, 7 milliamps leaving to the right, so our current coming down from the bottom has to be the remaining 3 milliamps. So this is Kirchhoff's first rule. It's not really numbered, his rules, but it's the rule that deals with current. Current going into a junction equals the current leaving a junction. Kirchhoff's second rule deals with voltage drops. Now we've talked before how voltage will drop as it goes over a resistor, but we've also talked about how batteries can increase voltage or decrease voltage depending on the direction they're facing. Essentially what this means is that we can add up all of the voltage drops in a loop, and then those voltage drops have to equal 0. Let's evaluate this circuit moving in a clockwise direction. So starting from our bottom right corner, we have a voltage source that is pointing to the right, so that means that's going to be a negative 2 volts. Then we have a voltage source pointing to the left in the same direction we're traveling, so that's positive 3, so that it gives us a total of 1 volt at that point. Then we continue and go across a positive 4, because again, this isn't the direction the current is going, so we end up with 5 volts at the next corner. Then we have some sort of resistor that had some sort of voltage drop, and then we end up back where we began. Because the sum of the voltage drops in a loop has to be 0, we know that the voltage drop across this mystery resistor is 5 volts. Now, these rules may seem familiar, they may seem similar to other things that I've said in the past, but these are the formal rules that you should use when trying to evaluate combination circuits. So let's try to apply them to that circuit that we were just dealing with. So here's the same problem that we were working with before, but we've added this resistance 1, 2, 3, 4 that we solved and the total current that we solved for. We know that the total current is the current leaving the battery. So first, let's use the junction rule to figure out how much current is going through R4. We know 0.06 amps has to somehow be split between this top route across R1 and between R2 and R3. And we don't know what those ratios are, but we know that that split, they're going to recombine back together when they cross across R4. So we know that the current going through R4 is going to be the same as the current leaving the battery of 0.06. So we can figure out the voltage drop across R4. V equals IR, we have I, we have R. We calculate that V4 is equal to 4.2 volts. So now that we figured out the voltage drop of R4, we have to flip back and use our other Kirchhoff law that talks about the voltage drop in different loops. Now, one thing that wasn't described very clearly in the previous slide is what a loop is. So here, there's actually 2 loops that are occurring. So one loop that just goes across R2, R3, and R4 and uses the battery, and then a second loop that skips R2 and R3 and instead goes across R1. So a loop is essentially just a mini series circuit that is contained within your circuit. Let's start by evaluating this top loop that uses R1 and R4. We know that our total voltage, 9 volts, has to dissipate across R1 and R4 because the total sum of the voltages has to be 0. We set up this equation and solve for V1 and find that our voltage across R1 is 4.8. Now we've figured out the voltage drop across R1, and we're going to have to use that value to figure out what the voltage drop is across R2 and R3. But in order to do that, we're going to have to go back to our current evaluation. So first, let's figure out what the current going through R1 is. A simple Ohm's law calculation will tell us that the current is 0.02 amps. Because we know that the current going into this first junction is 0.06 amps, and we know that the current that goes across R1 is 0.02 amps, the current going through R2 and R3 has to be the difference. So we can use these currents to now figure out what the voltage drop is across R2 and across R3. Using Ohm's law, we can figure out the voltage drop across R2. We work that out and we see that it is 1.6. Doing a similar calculation, we can figure out that V3 is 3.2 volts. Now when we look at this, we can see this is not only consistent with Kirchhoff's law, but also consistent with what we've learned about parallel circuits. So first, let's look at the total voltage drop that we see in this top loop. Yes, these three resistors count as a loop. We have 4.8 volts that's dropped over R1, and then because when we're working backwards, we add stuff, add the voltage drop across R3 and R2, the sum of which is 4.8. So the total voltage drop across these two parallel circuits is 4.8 on the top, 4.8 back on the bottom. And then when you look at what we talked about with parallel circuits, the voltage drop across parallel circuits is always going to be the same. The voltage drop across 2 and 3 is the same as the voltage drop across 1. All of this is consistent, and these rules, these Kirchhoff rules, allow us to get these values. First, before we get talking about the quiz, I want to briefly apologize for the inconsistency of the audio sound. I got kicked out of like 3 different rooms in the library trying to record these last 2 slides. Anyway, here's your quiz. First, we have the same circuit we've been dealing with, R1 on the top in parallel with R2 and R3, and then R4 in series with those two parallel. R1 is 240, R2 is 40, R3 is 80, R4 is 70 ohms. First, what's the total resistance of the circuit? Second, what is the total current leaving the battery? And third, if 0.02 amps flow through R1, how much flows through R2? A little hint on that you can think about Kirchhoff's laws. So go ahead, fill out your quiz sheet, and I will see you all in class on Tuesday.